We've done the volume for solids of revolution using the disk method. What's the washer method? Let's take a look at that first example where we had the parabola and the axis of rotation was the axis of revolution. I'm going to revolve our region to remind you of what that looks like. Okay? I'm going to reset this picture, and now I'm going to move the axis of revolution so that it's not touching the region that is shaded. See how there's a gap between the region that is shaded and the axis of revolution? Now I'm going to revolve that region. And do you see what's been created? Each of the slices now is still circular, but there's a hole in it because there's a hole in this region from the gap between the shaded region and the axis of revolution. So now let's think of the volume in a similar way. And I want you still to see this picture. Well, remember that we said the volume is the area of the slice. Well, the volume is still the integral of the area of the slice, just like it was before. But now, what's the slice? It's still circular. Let's take a look at it from a front view instead of a more side view like that is. There's a hole in it. So we're finding the area of just this region that I'm shading in right here. How do you find the area of a washer? Basically a circle that has a hole in it. Well, you take the area of that big circle, pi r squared. I'm going to call it big R because it's a bigger radius than the little circle. And you take the area of the little circle. Let's draw it like this. I'm going to draw its radius just in a different direction so it doesn't overlap, and I'm going to call that radius little r. So that area is pi little r squared. I should probably define these differently. Area of the big circle and area of the little circle. Well, I want to take away the area of the little circle. So ultimately I'm saying pi big R squared, the area of the big circle, minus pi little r squared. So where my volume is still the integral of the area of a slice, now my slice is a washer. So it'll be the integral of pi big R squared minus pi little r squared. Or, because both of these have pi in it, factor out the pi, and it's just integral of big R squared minus little r squared, and then we can multiply the pi to it at the end. So that's basically it. You've worked with the disk method. The washer method is just like that, except there's a hole in the circle. So think of it like big circle with a hole in it. We want this area that I'm shading in right here. So we have to find the area of the big circle. That has a big radius. Call it big R. So that's pi big R squared. And then we have to take away the area of the little circle. Call that pi little r squared. So you get the pi, which can be factored out and written on the outside, times big R squared minus little r squared, and it's still volume is the integral of the area of a slice. It's just that this time our slice happens to be a washer. Otherwise, everything is exactly the same as the disk method. Let's look at a few examples. Always we start with drawing our region. Find the volume of the solid generated by the graph bounded by y equals x squared. 0, 0. I wanted to maximize the picture that we have. So notice how I'm counting differently on the x and y axis. So over 1 and up 1 actually is here. Over 2 and up 4 actually is here. So I'm going to graph this parabola. maximizing our space so that we can see it quite clearly. The line y equals 4, and that's all they described, so I will shade in that region. And as you've noticed, I like to use a slightly different color for the shading so that you can tell where my original curves were. Just like with the disk method, I draw my axis of revolution. Well, it's the x-axis, so I'm going to trace the x-axis and show my... So I've drawn my axis of revolution and my little swirly. Then I draw my reflection. So I've got 4 units, 1 unit, 4 units. That looks about right. I've got like this, I've got like this, I've got the horizontal line, and I've got light reflection shaded in. How do I slice? Just like with disk method, perpendicular to the axis of rotation. Now I don't like to slice down the middle because I don't want to be misled that there's no hole in this. I want to slice off center so that when I picture one of these circular cross sections, I can tell that there is a hole in that cross section. So I know that I will be using the washer method. Therefore, I have to find 2 radii, big R and a little r. Now, just like the disk method, if my axis of rotation is horizontal like the x-axis, I'm going to be working with respect to x. Just like with the disk method, if I'm working with respect to x, my radius is measured top minus bottom. So the top of big R, let's write down that we're working top minus bottom. Top of big R is the line y equals 4. Bottom of big R is the line y equals 0. Little r, well, this was big R all the way to the outer edge of the solid. That was our big R. Our little r, perhaps I make it a different color to see it a little bit easier, from the axis of rotation, but just filling in the gap that is blank, not the shaded region. Our little r also top minus bottom, the top being the parabola. So the top is y equals x squared, the bottom being y equals 0, or just x squared for short. Now remember, volume is always and will always be the integral of the area of a slice. This time the slice happens to be a washer, so we're going to say pi integral big R squared minus little r squared. And we've determined that we're working like the x-axis of rotation, so it's with respect to x. So my integral will be big R squared, 4 squared, minus little r squared, x squared squared. Our limits go from the lowest x value of our region, 1, 2, 3, 4, negative 4, to the highest x value of our region, positive 4. Perhaps you simplify a little bit to find this volume before taking the antiderivative. Either way, we solve for this antiderivative and we get 256 over 5 times pi. Uh-oh, I just noticed that these x values are not negative 4 and 4. How do we get to y equals 4? 2 squared. 2 squared makes 4. So this should be 2 and negative 2. So let's fix those limits. Negative 2 to 2. Negative 2 to 2.